By the end of this video, this solar panel will charge a 12-volt battery, and that battery will run a real 230-volt load through a 300-watt inverter. But before I switch anything on, I want to show you not only what connects where, but why every breaker, fuse and cable is here. If you need a solar system like this, watch until the end. Welcome to a new series where I'm building a small home solar power system from individual parts, and then upgrading it step by step until it becomes complete overkill. Today we are starting with the very basic version. I'll take you through the layout, wiring and protection, then power it up in a controlled order. Check the important voltages and see whether it can actually run a lamp or a fan. This is a demonstration of the system architecture, so the ratings and wiring still need to match your own equipment and local requirements. Before touching a tool, let's make the energy path easy to follow. The panel supplies the charge controller. The controller manages charging of the 12-volt battery. The positive and negative bus bars give us a clear distribution point, and the inverter converts the battery's DC power into 230-volt AC for the load. The breakers and fuse let us isolate sections of the system and protect the wiring when they are correctly selected. This is the point where a basic system can still be built faithfully. On the solar side, I am using a DC rated breaker, and the battery branch has its own DC rated breaker plus a fuse close to the positive battery terminal. The words DC rated matter. A normal household breaker is usually designed for AC. Alternating current passes through zero every half cycle, which helps an arc extinguish when the contacts open. Direct current has no natural zero crossing, so a breaker designed for DC needs a suitable contact and arc quenching arrangement. I never assume that an AC breaker is safe on DC just because the current rating looks right. I check the DC voltage rating, current rating, pole arrangement, interrupting rating, and any polarity marking. The numbers in this build are specific to hardware and cable. They are not values to copy blindly. I start with the mechanical layout, not the wiring. I want the energy path to be readable from left to right, the high current runs to stay reasonably short, and every terminal to remain accessible for inspection and tightening. The controller needs space around it, the covered bus bars sit near the center of the DC system, and the inverter is kept where its DC connections and cooling surfaces remain unobstructed. A clean layout is not only cosmetic, it makes polarity mistakes easier to spot and future maintenance much less confusing. All sources remain disconnected while I build the wiring. Both breakers are open, the battery is not connected, and the panel is not connected. Before a conductor goes onto the board, I cut it to length and fit the correct termination, ferrules for the clamp terminals and ring slugs for the studs. The ferrule or lug must match both the conductor size and the terminal, and every crimp gets a visual check and a firm pull test. The panel positive and negative conductors enter the lower side of the 16 amp DC breaker, and the upper side continues to the solar output of the PWM controller. The controller's battery output then connects to the positive and negative bus bars. The battery branch passes through the 32 amp DC breaker before reaching those bus bars. From there, the inverter has a clear positive and negative supply. I keep the color coding consistent, but color is only a visual aid. Polarity will still be confirmed with a meter before energizing anything. 12 volt sounds harmless, but a lead-acid battery can deliver a very large fault current. That is why the positive cable receives a fuse as close to the battery as practical. The goal is to minimize the length of the unfused cable. This build uses a 60 amp fuse, but the correct value must protect the cable and stay within the limits of the connected equipment. It is not chosen only from the inverter's label. For perspective, 300 watts at 12 volts is already 25 amps before inverter losses, so cable size, connection quality and protection matter. With every path complete, I secure the cable runs and add clear labels to the breakers, busbars and battery fuse. Labels do not replace measurement, but they make isolation, inspection and future troubleshooting much clearer. With the mechanical work complete, I install the battery cables and the fuse holder, keeping the protective devices open. Before closing anything, I check that positive reaches the positive and negative reaches the negative. The locks are secure and no loose strand can touch an adjacent terminal. The connection order must follow the manual for the specific charge controller. Many controllers that automatically detect system voltage require the battery to be connected and recognized before the solar input is enabled. I follow the sequence specified for the controller, verify the detected voltage and only then enable the PV side. This is where I deliberately slow down. Before power up, I check 5 things: polarity at every source, the expected voltage, secure cable locks, open breakers and covered live distribution points. I also make sure the inverter and its AC load are switched off. Only after those checks do I energize one section at a time. First, I enable the battery side and confirm that the controller powers up as expected. Display now shows a sensible 12 volt system value. Next, I verify the panel polarity and voltage, then enable the solar breaker and look for a charging indication. I measure at the battery, the bus bars and the inverter input. I'm not looking for one magical number. I'm checking that the polarity is correct, the readings are consistent, and there is no unexpected voltage drop before a load is connected. The build is complete, but a neat board is not proof that the system works. This test needs to answer 3 questions. Does the controller remain stable? Does the inverter receive the correct DC voltage? And can the system run a real AC load without the voltage collapsing? I switch on the inverter with no AC load connected, confirm that it starts normally, and that at the lamp. The light gives an immediate visual result. Next comes the fan, which adds a motor load and makes the test more meaningful than a display reading alone. The loads are running, the input voltage remains stable, and the PWM controller continues to show a healthy system voltage. That is the proof this first build was meant to provide. So this basic version now has a clear energy path. DC rated isolation, battery side overcurrent protection, covered distribution points, and a successful reload test. More importantly, we did not jump from the loose part straight to the power switch. We planned the layout, built the energized, checked every section, and then power it up step by step. This is still a demonstration board, not a finished permanent installation. A permanent system would need enclosure and strain relief decisions, protective battery terminals, verified cable sizing and torque, and an AC earthing and residual current protection strategy that matches the inverter manual and local rules. In next parts, I can build on this basic system with better monitoring, improved protections, and a more installation-ready layout. Next time, I replaced the PWM controller with an MPPT controller. On paper, it should be the obvious upgrade, but the result isn't what you might expect. For some reason, the MPPT controller produces almost exactly the same power as the PWM controller. So what's going on?